So I'm Amit, and today I'll talk about on-shell methods in geometry of scattering amplitudes. Even though the title looks too technical, I assure you that the talk is going to be non-technical, and I'll gloss over all the technicalities, so experts in the audience, please pardon me. And I've made sure that all the, wherever there is a bit of jargon, I've marked it as a purple color, so you can just tune it out if you don't care about high energy physics. Yeah, so what is scattering? So, well, moving things collide and deviate from their original path, and that's scattering. So for instance, billiard balls, they move, they collide, and they deviate from their natural path, so that is scattering. Or someone throwing a rock at me, so that will be an example of a scattering process, okay? So what does it mean to solve a scattering process? So in simple classical mechanics, we'll solve for the outcoming momenta and using the momentum conservation and Newton's laws, and that will solve the scattering process for us. But nature is quantum mechanical, and in quantum mechanics, we can't solve for outgoing momenta. So that means we can only talk about probabilities. So amplitude, or a scattering amplitude, that squared gives us the probability for that particular outcome to happen, okay? So for instance, if we have two electrons with momenta P1 and P2, and they scatter off each other, so the probability that they come out with momenta P3 and P4 is the mod square of this quantity that we are going to talk about here. So how do we calculate these scattering amplitudes? So quantum field theory is the usual way to do it, and what we do is we calculate correlation functions. Okay, so so in quantum field theory, particles are merely excitations of the quantum fields, okay? And you have, for instance, this phi field can be said to describe the electron field, and if that is the case, then we find such 4-point correlation functions, and the one particle pole of this correlation function will compute the 4-particle amplitude for us, okay? And yeah, so for instance here, if we take appropriate poles and residues of this guy, we'll get the 4-particle amplitude here. All right, yeah, so one of the key concepts in QFT is the presence of virtual particles or off-shell particles. So that means that their energy squared is not equal to momentum squared plus mass squared, okay? And they act as the messenger for interaction. So for instance, electromagnetism is mediated by photons, okay? So we draw these kind of diagrams and we compute these. These diagrams are called Feynman diagrams. You might have seen them here and there. And yeah, so that is how one would usually compute amplitudes. So today I'm going to talk about strong nuclear forces. So that is one of the 4 fundamental forces, and QCD, quantum chromodynamics, dictate the dynamics of the strong nuclear forces. So just like photons are the mediators for electromagnetism, gluons are the mediator for strong nuclear forces. And now let's say that I want to calculate a 4-gluon amplitude, okay? So I'll draw just like this. I'll draw all the diagrams that can contribute to something like this, and that is 4 such diagrams, okay? And after doing some calculation, what gets an answer like this, okay? So here notice that just like photon has 2 polarizations, you know, the usual polarizations like circularly polarized light and all. So gluons also have polarizations plus and minus. So for this particular polarization configuration, we get this answer, okay, where these symbols mean this. So you take momenta P1 and you dot it with the P2, and then you get this angle bracket thing. These are called spinor helicity variables. We don't need to worry about them, yeah. So now this was a 4-particle amplitude, and now if I want to calculate higher point amplitudes, let's say 2 to 3, 2 to 4, and so on. So the number of diagrams that contribute to process keeps increasing. So for instance, if you have this process, then you'll have some 25 diagrams and 220 diagrams and so on. And these are not just for academic purposes, like these are used in actual collider physics and all, so people do care about how to calculate them efficiently. So for instance, if you want to calculate 2 gluons going into 8 gluons, the number of such diagrams will be more than 1 million, and all of them individually will be very complicated to calculate, okay? You wouldn't actually sit down and calculate each one of them. So this was 2 to 2 amplitude. So now next, if we add up these 25 such diagrams, the answer actually turns out to be this, okay? It's neat and simple, And what happens is that for any number of external legs, the answer is just this. So even if you have million, billion diagrams, they just somehow add up, and the answer is just simple, neat expression like this. So this is very unexpected, and the usual QFT will not know why that is happening. So that means there is some underlying hidden structure or something that the usual Feynman diagram techniques is missing. Okay, so why are the amplitudes simple, and there should be a simpler way to actually calculate them. So the inefficient way is inefficient because the action principle has redundancy due to field redefinition and the choice of gauge and so on. Okay, so but a scattering amplitude is independent of all of them. Okay, so to bypass this, what we do is something called on-shell methods. That means you use lower point amplitudes to build up higher point amplitudes as a recursion. All right, so this is based on the idea of factorization, that you take 4-point amplitude, let's say, and if you take a particular residue of it, then it decomposes into a 3-point amplitude and 3-point amplitude. Okay. So a systematic way to do this is called BCFW, and that's a vast subject on its own now. Yeah. So now let's move on and look at a more complicated amplitude. Okay. So if we flip one of the polarizations, so for instance, this one we saw if all of them are plus, 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 plus. Okay. But if we flip one of them, we get horrible expression like this or this. So now this, these two are supposed to be equal, but they don't look like it. And now can we ask, like, why do they look so different, or is there something more to it? Like, is it just a bunch of algebra, or is there something more to it? So what happens is that something very neat and very surprising, like nobody expected it, but this amplitude, this answer, and this answer is actually volume of a 3-dimensional object, this one. So I'm not oversimplifying it in any way. So this amplitude actually is volume of a polytope in CP3. So actually this term corresponds to the volume of this tetrahedron. And imagine this tetrahedron and chop off its top, that is this small little thing. So then if you take the difference of the volumes of 2 tetrahedron, you get the volume of this shape. Okay, and you can also triangulate this shape into 3 tetrahedrons in a different way. Okay, so you can convince yourself that there are different triangulations possible for this polytope, and actually these different looking representations are merely different triangulations of the same polytope. Okay, so this is very surprising and unexpected, and actually it led to a whole lot of more things in later on. So what happens is that higher point amplitude correspond to volumes of polytopes with higher number of faces. So for instance, 6-point correspond to a polytope with 5 faces. So 5-point amplitude correspond to volume of polytope that has 4 faces, that's a tetrahedron, and so on and so forth. Okay, that is very unexpected, and yeah, and technically these polytopes live in CP3 spaces, and these are the coordinates are momentum twisters and so on. And this is a well-known result since I think 10 years now, and what we are trying to do is do something for massive particles. Yeah. So the simple nature of Park-Taylor amplitude, this one is called Park-Taylor, and this polytope picture, sorry. So this is due to the underlying conformal symmetry of this Yang-Mills theory, that is QCD at tree level. Okay, and the full quantum theory does not have such a symmetry, and the only reason that such nice properties are there for Yang-Mills is because at tree level, the usual gluon theory is actually same as this n is equal to 4 super Yang-Mills. That's maximum number of supersymmetry that you can put on a Yang-Mills theory. Okay, and this n is equal to 4 super Yang-Mills is special in many ways. It has a lot of symmetries. It is termed as the simplest QFT, and it is a low energy effective theory of a string theory, and so on. So this polytope picture, such things actually led to this was a precursor to the amplituhedron in this n is equal to 4 super Yang-Mills, where you can write all the loop amplitudes and everything as volume of some nice polytopes and geometric pictures and everything. And about what we are trying to do is we're trying to calculate some amplitudes in this n is equal to 4 theory in some massive phase. And that's it. Thank you.
Thanks a lot for the beautiful talk. So any questions?
So these actually need conformal symmetries, right? So what happens if you have a strongly interacting theory but you're near a phase transitions? Can you calculate like different kind of free energies or something using these techniques?
I think the questions that we are asking here are in perturbative theory because we calculate scattering amplitude, and if you are near a phase transition or something, then
But if you
Yeah.
use only the CFT as
Yes.
the underlying principle,
Yes.
whether that helps
yeah.
in calculating?
Yes, I think people have studied, people must have studied n is equal to 4 planar as a CFT, and they would have calculated a whole lot of quantities.
What
which
about
I'm-
in normal quantum field theories,
Normal quantum field theory? As in,
near phase transitions?
I don't think I'm aware of a lot of literature in that area, sorry. Yeah.
Thanks.
Okay, if you don't have any more questions, we'll move on to the next speaker. Before that,